Yes, thank you. Let's start relatively promptly. We start a session with 4 talks, and the first talk is by Adrian Perik from ETH Zurich. And I like to give long introductions, and I think Adrian is making it very difficult because if he has so many permanent items on his on his bio. So, but try to keep it short. He got his bachelor's at PFL in Switzerland. He went to US, and he was in top schools. He got his degrees at CMU, but for various advisory reasons, he spent a stint at Berkeley. When he was graduating, looking for a job, I had the distinction to actually interview Adrian, his significant other at that time, at UT Austin, but he continued further, and he did great at CMU, but regardless, he decided to come back to Switzerland, and now he's at ETH. And at some point, that he was the person who single-handedly brought network security into CCOM and published a number of papers on the topic. And CON is a project that many of you might know because your email address was on a mailing list, so occasionally you probably received some mailing newsletters about the project.
Yeah, thank you so much, Sergey, for the introduction. Very nice to be here, and let me tell you a little bit about Scion. So Scion is a new next-generation internet architecture, and it has many different aspects to it. So security, of course, is one very important goal, but also other things are important, such as it provides support for path-aware networking. So the sender knows the packet's path, and this enables a lot of interesting properties, such as geofencing. You can know where a packet goes through, you can know where a packet does not go through, and it also enables multipath communication. So here's some word of caution. When you experience multipath communication, it's quite addictive. So once you have it, you don't want to live without it. So, and in today's internet, you cannot get multipath in a clean manner. And so be careful when you do experiments with multipath. Also, the communication is highly available. It's secure. The whole architecture is secure by construction. And the goal is ultimately to achieve internet communication that's free of BGP, so not to need any of the traditional BGP routing. And it also improves a lot of aspects of network operations. It provides higher network utilization, more advanced traffic engineering, and so on and so forth. But so these are the core properties. Let me tell you a little bit more about the architecture itself. The main design goal is to achieve very high levels of availability, even if parts of the network are actively malicious and want to prevent you from communicating. So even if the adversary controls some autonomous systems or routers, you should be able to communicate as long as an attack-free path exists. By the way, this is really loud. Could you turn this down a bit? Right. Yeah, it's too loud. I'm trying not to get feedback. It's not too loud? Okay, because I'm feeling there's almost feedback. All right, so high availability is the main design goal we aim for. And then also other design goals are secure entity authentication that scales to our global heterogeneous environment. So we know in the world we don't have a single trusted party, so how do we design public infrastructures without having a globally trusted entity? Trust should also be flexible in that different entities should be able to select whom they want to trust and whom they want to rely upon. Operations should be transparent, so it's very clear what happens in various aspects of the architecture. Controls should be more balanced. The sender should have some amount of control as well as the receiver. And of course, ISPs also need network control. Finally, we want scalability and efficiency. And from the previous talk, of course, flexibility we claim to have. Now we can talk about if, with this evaluation framework, how much flexibility SAN really enables. In any case, I can say that scalability and efficiency is at the level of today's internet, if not better than that, despite all the security mechanisms. So let me briefly give you an overview of the control plane and the data plane, and then I'll talk a little bit about deployment aspects. So one concept in Scion is the concept of isolation domains, where we essentially group autonomous systems into areas of entities that can agree on a root of trust. So we see different circles on this slide here. The small circles represent autonomous systems, and then the larger gray circles, they're the core ASs, the ASs that manage the isolation domain and essentially issue the routing beacons and so on. And then the larger circles represent this construct of the isolation domain. Then we have this trust root configuration, which essentially represents the roots of trust valid in this isolation domain that is then used for all the security operations. So for the public key infrastructures, all the basic keys are part of this TRC. So what's important here is that each isolation domain can themselves define what their roots of trust are. And so they don't have to be the same. So typically they will be quite different across different isolation domains. So we have autonomous systems, core ASs here in this gray area. And also what's interesting is this isolation domain concept is a virtual concept. So one entity can also belong to multiple isolation domains, as we see of the one here on the right. All right, so let me briefly walk you through the basic operations of Scion. And I won't be able to go into too big a detail, but I hope in 25 minutes you see some of the flavors of the architecture. So to discover paths, what we do inside an isolation domain, we send out these path construction beacons, PCBs, and they're essentially represented by these yellow squares that go through the network and trace the network path that they've taken. So it's not unlike a BGP type update mechanism where the path is being traced. What's different is that these updates are only issued by core ASs, and the other ASs simply forward them. So there's no explosion or like in today's internet where every AS floods the whole world with these beacons. So it's a path-based architecture, so we see different beacons that traverse the network, create these different paths that are being identified and communicated this way. So an entity who receives one of these paths can now use these paths in order to send packets to the core AS or to ASs on these paths at this point. And there's a lot of cryptographic aspects as well. Just very briefly on this slide, I wanted to highlight that there's a very efficient symmetric key mechanism built into what we call hop fields. These fields are then added to the network packets to traverse the network. And then there's also digital signature to then verify these beacons. And one is very fast and efficient to verify, but can only be verified by the AS that issued this PCB and this hop field. But the signature then allows any destination or any verifier to check all the information in the beacon. Now, the same mechanism essentially also happens across core ASs, and here we see a beacon going out from AST. The different beacons traverse the network, and again, like before, different paths are being identified in this way. Now, what's different in Scion is these paths are being found, then they're being registered at path servers at various places in the network. So first, the local hosts inside an AS need to know how to get to the core of the network, and there's a local path server that stores these what we call op paths to get into the core. And so in Scion, what's possible is to select the paths that an entity wants to announce, and also suppress some paths that may be not as good as others. And so in this case, all 4 paths are deemed to be good paths, and they're locally registered. Now all the local hosts can use these paths to get to a core AS. A similar concept is, though, to tell the paths to the rest of the world. And what we do here is that, again, the paths are being selected by the autonomous system, and then one path is deemed to be not as good. Maybe it's not very reliable, or maybe it's more expensive, or has some other attributes that are undesirable. So this path will be deleted in this example, and then the other 3 paths are good paths, and then they're being registered at the core path server. So at this point, anyone else in the internet can fetch these paths and can then communicate with S. Now, what Cyan also allows you to do is to use multiple network links. So the granularity of the forwarding information is based on the ingress and egress interfaces of ASs. So we see here between L and O, there are two different links, two different network links, and they're being identified simply by a local identifier. And what Cyan then allows you to do is to specify specifically, I want to be on this or the other path, and select these egress interfaces as explicitly. And this, of course, is assuming that the paths are available. ASO may reserve one path only for ASS or for ASQ, and may not give that information onto R. These are all different types of opportunities that Cyan enables. All right, so this was already it for the control plane. Let's take a look at the data plane, how it works. We support a path lookup, not unlike today's DNS system, but what's different in Cyan is, well, we have a system called RAINS to do this name server lookup. It has a lot of similarities with DNS, but many of the issues are fixed. So what RAINS returns is the isolation domain and the AS number of the destination host. The address then is almost completely unimportant in Cyan until the packet actually gets to that destination AS. So then the host contacts a local path server to look for different path segments to get to that other isolation domain and that autonomous system. And the path server returns up path. These are the local paths to the core, the down paths at the destination site, and then also core paths connecting the two entities. You can imagine that the core paths are the paths in what we call the internet core, essentially the largest ISPs, essentially connecting the ISD's core ASs. Now the host has a lot of different options to combine these path segments. And typically we expect that we'll have about 10 or so different paths, depending of course on the network topology and on the distance of the different, of the source and destination. But we do believe that there will be a number of different paths that can now be selected by the end host and constructed by combining these different path segments. So here's an example. We have a host in R who wants to communicate with a host in S. So the source host looks up the different paths, obtains the blue up paths and the green down paths at the destination. And also, because not all up paths are connected to all the down paths, the corresponding core path segments to form those connections. Now the host has a lot of different choices. So of course a good choice is to use one path to go to O and then a green path to get to S. So we call this a shortcut. And so the important point here is that it's not always necessary to go back into the core, then all the way back down to get to the destination. Also, we can make use of peering links, and we support peering links with exactly the same semantics as they're used in today's internet, and to retain all those business constructs in Cyan, which is very important for adoption. We then also have additional choices. So this path is not as interesting because it's longer and is covered by the other two shorter paths. But another interesting path is this one going all the way around because it's completely disjoint from the shortest path and traversing other interfaces. So in Cyan, all these different paths can be used at the same time, and it's really nice. It's as I'm telling you, it's quite addictive when you have this ability, and when you see this working in operation. It provides a high level of availability, and also allows you to do optimizations if some paths have higher bandwidth, other paths have lower latency, and so on and so forth. It gives you many exciting choices. The same operation here works also in the case of remote ASs. Here we need a core path to connect the up segments with the down segments. And in this example here, we also have different paths because there are different connections, in this case between M and T, but also providing some level of diversity. The path construction itself, essentially, once the network paths are obtained, they then get put in these in the packet header, and that's probably the biggest disadvantage of Scion that information has to be carried. So each hop field utilizes 8 bytes. And so for every AS hop being traversed, we need to spend these 8 bytes. Also, the info fields have 8 bytes. In this example, there will be 80 bytes added to each packet, which is a lot of information. However, we believe that given all the benefits, that's the price that you need to pay for. So as a summary of the architecture, Scion essentially is a complete redesign of the network that solves a lot of fundamental problems like BGP convergence issues. It separates the control and the data planes. It isolates mutually untrusted control planes and so on. So the way to think about Scion is it's really an isolation architecture for the control plane, but then in the data plane, it's really a transparency architecture so you can see exactly what happens to my packets. So that's this overview. So let me go on with deployments and tell you a little bit about what we've done to utilize Scion in the real world. So here's a high-level network diagram of the deployment at ETH. So in Switzerland, we have an ISP for all the academic institutions, and their name is Switch. So it's not the network device, but that's the name of that ISP. And Switch also is running actually 2 Scion networks, a research type network to which ETH is connected, but also a commercial Scion network where some real customers are already starting to use this technology. And here for the research side, we added these green boxes which represent Scion routers. And you see, depending on the connectivity and on the distance between the different Scion routers, we either use another cable, like in the left connection to switch, or in the right connection, we reuse the current IP connectivity to get from one Scion router to the other router. And also between Swisscom and Switch, they're peering at 2 data centers, so they're actual dedicated connections for those other 2 connections between Switch and Swisscom. So you see now within ETH, actually anyone can make use of Scion by using the local IP connectivity. So essentially we're adding IP headers to Scion packets, and those IP headers then get removed again at the border router, and so on and so forth. So as the Scion packets go through the network, IP headers are being added locally to provide local connectivity to get removed again when the packet goes to the next border router. If internally you have MPLS or other network technologies, we simply essentially reuse the local communication fabric to provide connectivity, which then allows now anyone quite easily to upgrade and use Scion. So with these 2 border routers, Scion border routers at ETH, anyone at ETH can now install Scion on their system and use it without making any other local changes. So there are a lot of ways to use this technology, and I need to stay on time. But we have a Scion IP gateway, which essentially translates regular IP traffic into Scion traffic if the destination also has the corresponding Scion IP gateway. So in orange, we see these SIG boxes. And if a packet now, a network packet can be a standard IP packet, goes from between networks A and B, then they get encapsulated in Scion and the Scion network is being used. Otherwise, the packet goes through as a normal IP packet. So this is the standard deployment that all the companies that use Scion put one of these Scion IP gateways in their networks. And we also are looking now at carrier-grade Scion IP gateways where we would support models where an entity B can also make use of Scion even though they're not an AS themselves. And so several banks are looking at this model for their ATMs, connecting ATMs to this network, and so on. So here are some more details how this works. So one also major project where we invested a lot of time in the last 2 years was a project called Scion Lab, where we said, let's make Scion very easy to use to the research community. And we created a global testbed for anyone to make use of. And in essence, it's really easy to make use of. This diagram shows that at the bottom, this depicts a normal computer, can be a laptop. And then you can create your own autonomous system on your local system and then connect to the actual Scion network. And you have a real autonomous system that you're getting that really participates in the routing and so on and so forth. So this is the current ScienLab network. You can go to our to this URL to get an updated view of this. And David Hauser at the University of Magdeburg also has done a lot of work and is we're closely collaborating on this with his group. So here you see all the different machines that we've deployed all around the world. There are a couple of noteworthy points. For instance, in South Korea, we have quite a large deployment in a testbed called KISTI that spans the South Korean research network and a number of other nodes across the world. What's really exciting is that this simple topology allows you to create a lot of different multipath opportunities. So we set up nodes inside the Amazon AWS data center, and that allows you to also make use of this infrastructure, so you can select a path into this AWS infrastructure. It gets then internally forwarded, and at the other end comes out to get additional choices for the multipathing. Another exciting aspect is you can select which way you want to go around the world. So in today's internet, if you send a packet from Europe to Southeast Asia, for instance, oftentimes these packets go across the US. They first cross the Atlantic, then the US, then the Pacific, to get to the destination. But this obviously creates quite high latencies. And in Scion, you can select if your packets would go that way or go the eastern route, which has much lower latency than going the other way. And so we've observed with the ScienLab topology already today that we can achieve lower latencies in some cases than in today's internet. So here's a use case how to make use of this infrastructure. You can make, we've talked to several blockchains to use this, so you can use the current internet, of course, but if there's a failure, we've observed that it's possible that ScienLab still provides connectivity and then allows you to achieve still connectivity despite the internet outage, even though we're using this overlay network. There's also commercial Scion network that is run by Deutsche Telekom, Swisscom, Switch, and Init7. Init7 is a smaller Swiss ISP that operates in the region of Zurich. And so there are several connections already, corporations that use this network. Several banks and the Swiss government is now starting to try out this infrastructure. And what's exciting is that one large Swiss bank has cut the internet connection of one of their branches last August, so August 2017. And for 1 year, that branch was only connected to the data center with and across this commercial Scion network. In the meantime, they've taken a second bank, and that was a much larger site that is also connected via Scion, and now they want to take 8 more branches and so on. So they're very happy with the properties they're getting. So I see Sergey is getting nervous, but let me just briefly tell you how can you obtain a Scion connection. So you can simply go to ScienLab, and there you can get an AS, a VM up and running with all the cryptographic credentials, essentially auto-installs, and takes about 10 minutes to download everything and for it to get started. But you just need to click a few keystrokes to get to that point. So it's very easy, low overhead to use that infrastructure. As a university, you can today get a Scion connection via Switch and also at DFN. David Hauser has started working with DFN to get a Scion connection. Also at the University of Bonn, there's a Scion connection via DFN. And so this is now also getting started. David Hauser also is working with Géant to extend the deployment there. If you're a corporation or a government entity, you can go to Swisscom and send me email. I can put you in contact with the people at Deutsche Telekom. You can contact Markus Seipel to actually get a Scion internet connection. So in conclusion, I think the biggest surprise also to ourselves is that it is actually possible to evolve layer 3. So a lot of people say, look, you cannot change the internet. This cannot work, but we've now seen that it's actually possible, and now ISPs are starting to get excited and started to get interested, and so early deployment is on the way. Of course, the reasons for corporations and ISPs to get interested is we have very strong properties for high availability communication. So we have multipath routing that is addictive, as I mentioned. It really has nice properties also to defend against DDoS attacks, to get high availability, and so on. And also, in some cases, you can, even with ScienLab, achieve lower latency than today's internet. We have exciting results also on the security side, where we can prevent a lot of the attacks, also do achieve DDoS defense mechanisms, and so on. So there's a lot to tell about this. To drive the commercialization, we have founded a startup on this, together also with 2 other professors at ETH. And so this is now getting started. They're called Anapaya Systems. So more resources are online. We've published a book with Springer Verlag last year. And the book the PDF is available for free on our website, papers, videos, tutorials, and so on. And the other links, the source code is open source. You can look at all this information. The core project team is shown here on this slide. This was last year's retreat, and this was this year's retreat. So thanks to all these collaborators, we can actually move this project forward. So thanks so much.
Some quick questions for... Okay, let's take these 2.
Very interesting idea. The question here is how much overhead you would bring by introducing this packet routing and let's say you have to introduce this kind of trace, let's say, states in the network. Right. So the granularity is likely based on flows.
Right. So actually, that's a great question. So it turns out the control plane is more scalable than today's internet. So we have a lot less work to do because we only have a very limited number of ASs that flood the network. And also the flood within is constrained within an ISD. Now for network state, it's my personal belief that we need to avoid any network state at all costs possible. So a lot of the time in the research in the last 5 years was based on how to make certain properties in a stateless manner on switches, because state introduces many security issues. And so even the most extreme case is that we have a quality of service system that provides per flow quality of service that does not have per flow state in the fast path on routers. And so everything I presented today has absolutely no state on any of the routers. All the router needs is one single cryptographic key. That's 128 bits, it's an AES key. And that's it. There's almost no other state in the routers. But then for quality of service, there are a few more things you need to do. But what we made sure is, and this took quite a bit of time and effort, to achieve very fast forwarding without having any per flow state in the fast path. So the router can very quickly forward this information. Also the Hornet system, our Tor replacement, super high speed and anonymity, without any state on the router. Right? So that's essentially all the things we do try to go in that direction.
So there is a very recent proposal in ITF about the AdPath, that you can actually use multipaths within the BGP. Are you aware of this, or do you? Right. How you compare with this basically?
Right. There's a lot of efforts going on, also segment routing and etc. There's I'm not familiar exactly with what you mentioned right now, but so Brian Trammell, the person right next to me here, he's sitting on the Internet Architecture Board, and he's quite closely involved in a lot of things at the ITF, and we keep in touch, and we've also now established a research group in the ITF for path-aware networking, where we are starting to standardize parts of Scion. So we're talking to several of these groups, and for instance, with the segment routing group, we've started discussion because we can provide a control plane also for segment routing potentially, right? An inter-domain control plane, right? So there may be lots of interesting aspects there.
In the internet, when they designed it, they also forgot to support mobility. Is that something that you think of, and which is better supported than the internet?
Right, I do believe that mobility will also benefit from these properties. Essentially, path awareness allows you to have multiple paths at the same time with your old address and your new address simultaneously. I think the hardest case in mobility is if you have two mobile nodes that communicate and at the same time they both lose connectivity. Personally, I believe that this case is extremely infrequent, right? Usually, one of the nodes retains connectivity while the other node loses mobility, and in that case, the new network address can be communicated on the old path. So then we do support ways to tell with a packet header extension to say, okay, here's my new address, and by the way, this is the same connection. In the case when really both entities lose connectivity at the same time, you need to do things like the Mobility First team has proposed at Rutgers University and other places, at UMass Amherst and so on, with their global name service. But I do think already the majority of cases are being covered by using, by having this multipathing ability and switching addresses ability.
Right at the beginning, there's a discussion about the core routing of these, the TRCs. Have you got any experience with those changing, because they're basically the building block? Right. Have you got any where they've had a property that's actually undermined them? Like, I mean, I appreciate no, because it's not that mature a technology, but how you might predict ownership change. Right. You know, I mean, every possible variant we can think of, nation changes, ownership changes, all these things have hugely affected ASs and DNSs.
Right, that's a really excellent point. We are getting to this point now. So in the book, we describe a number of ways in which these TRCs are being updated in case a catastrophic event happens, like Heartbleed, and suddenly all the private keys are being compromised. And so for these kind of cases, we also envision to have offline. So there's chapter 4 in the book that talks about some of these cases. We didn't talk about the TRC fundamentally changing, but the way we envision it, that they're threshold schemes that if you have a certain number of offline keys, then you can pretty much make any change to these TRCs. And a threshold of autonomous systems, and it's all defined. The policy, the update policy, is defined itself in the TRC itself. I'm happy to discuss this more with you, but in the absolutely worst case, let's say quantum computers come out and globally all the keys are being compromised. In that case, it would need some manual intervention where you say, okay, so we're going to roll to a new TRC version with all new quantum resilient crypto. And this is going to be now the new hash, etc. So we're thinking of ways to bootstrap this. But definitely we have prepared the whole system, all of SIAN is prepared for algorithm agility to start introducing new cryptographic algorithms while the old ones are also still in use. And so these things are already built in. But definitely it can get difficult in case of quantum computers or some really drastic events. Right?
Okay, let's thank again Adrian for the presentation.
Thank you.
It's in general, it's difficult to fill in, Adrian's shoes when you talk about writing security. I think our next speaker has an additional challenge. As I mentioned in the morning, Fontes Dimitropoulos unfortunately couldn't come because of a loss in the immediate family. So today we have a talk by Pavlos Sermpezis, who is a postdoc working on Fontes project in fourth Crete, and Pavlos graduated from Aristotle University of Saloniki, 2011. He went to France and got his PhD from Eurocom Paris Tech. And it's also about network routing security, but kind of in particular scenario of hijacking.
Okay, thanks for the introduction. So I'm Pavlos Sermpezis. I'm a postdoctoral student and representing Professor Xenofontos Dimitropoulos, who is a recipient of the ERC grant. Today I'm going to present you Artemis, which is a part of our work. It's a defense system against a security threat in the internet routing, and this security threat is called BGP prefix hijacking. So a little bit of the history of Artemis. Artemis started as work within the ERC Netvolution project, which is a starting grant awarded to Professor Dimitropoulos in 2014. And this work of Artemis, this specific work of Artemis, led to the submission and final the grant of the ERC proof of concept project, Philos, whose aim is to transfer the research of Artemis to a product. Now, a little bit more history about Artemis. So it all started in 2016 in a hackathon organized in Keida at UCSD, where some members of our group went there and tested some new tools, and this led to a SICOM demo in 2016. Now, since 2016, we are kept on working on Artemis, collaborating with some researchers from Keida, and doing from basic research up to a survey among network operators. So this led to the following publication, a CCR editorial paper, where we report our results about this survey among the network operators, the guys who work the networks, and our main publication, which is accepted in transaction networking and will soon appear. So let us see, let us see what all is Artemis about. So the internet today, the internet routing today is not secure and it's not reliable. Frequently, there are events like this reported. So for example, a hacker stole some Bitcoins and network redirected traffic from Visa and MasterCard through its own network. We don't know what it did with this traffic, but it redirected it. And even Google did a mistake and brought down the internet in the entire Japan, I think, for like 30 minutes. You can assume how big events are. Now, the common root behind these events is BGP prefix hijacking. So just a few, I'll give you the overview about what is BGP hijacking for those that are not familiar. So let's say this is the internet that is composed of other networks, and each network has blocks of IP addresses, which are called IP prefix. So Google advertises through BGP to its neighbors the IP prefixes, and everyone knows and sends their traffic to Google for this prefix. Now, because there is no authentication in BGP, another network, a network X, can announce the same prefix and pretend that this prefix is its own. So networks don't know and might send their traffic through this network. And this can cause an outage of a service of Google, or it can also lead to traffic interception if this network X forwards then the traffic to Google. So might be a man-in-the-middle attack. And as you can imagine, this can affect millions of users. These results are quite common and usually last 4 hours. And during these hours, networks lose money. And for some big companies like Google, the cost can be up to hundreds of thousands of dollars per minute. Okay, this is a basic problem in internet routing. So what people do for it? There are, in the past, there have been proposed several research approaches, like the one Adrian suggested before, which I find them quite elegant. The problem is that network operators are reluctant to deploy these approaches. So even, for example, RPKI, which is an approach which has seen the most adoption between these approaches, its adoption is still low, it's 8%. And in fact, we ask operators why you don't use this. So for example, for RPKI, they told us that, okay, it has little security benefits if it's not widely adopted, so we don't use it for that way, and also there are some costs, etc. Okay, so what do people, the remaining 90%, let's say, do about BGP prefix hijacking? Most of them rely on third-party services. So these services are some companies that monitor the internet, try to detect this kind of events, and if they detect an event, they notify their customers that there is a hijack. A lot of people use these services, but are not very satisfied as they reported to our survey, and the main reasons are the following. These services can detect only simple hijack types, and usually they send a lot of false alarms, and these false alarms, it is usually because they don't have full knowledge of what their customers do with their prefixes. So for example, if a customer announces a prefix in a different way, for example, for traffic engineering purposes, these companies don't know, so they send an alert. So the problem with this is that the network operator has to check manually each alert to see if it's traffic engineering or a malicious event, and then proceed manually to the mitigation. And all this manual process, it's time consuming. So as you can see from this graph, in most of the cases, these events last for hours, and this is a severe impact. And last but not least, because there are third-party services, there are also some privacy concerns of the network operators who have to share their routing policies, etc. Okay, so we said there are these problems of previous research approaches, these problems of these practices. How can we fix these things? So we designed a system which we call Artemis, which is a system to defend against BGP prefix hijacking. And this system is used by a network itself. So a network can use our system in its own network to protect its own prefixes, its own resources. And even if only one network uses it, it can protect for himself. So there is no need for collaboration with many networks. And what our system does, it does real-time detection of hijacks. And when it detects hijacks, it proceeds to automatic mitigation. So it does not only detect the problem, but also solves the problem. So the main advantages of Artemis compared to existing practices, first is that it can, we designed algorithms that can detect not only the basic types of hijacks, but all types of hijacks. So for example, if a hijacker is quite sophisticated, he would go with a sophisticated attack. So if you have a system that can detect only simple attacks, it's not enough. That's the motivation for this. Moreover, Artemis, by design, returns 0 false positives and false negatives, so 0 false alerts for most hijack types. And for the very sophisticated types, it has still low false positives. And in fact, the network operator can pre-configure Artemis so to receive alerts depending on the impact of the observed event, of the suspicious event. Moreover, Artemis is privacy preserving and flexible. It gives the operator the opportunity to control it as he likes. So the overview of Artemis is this. So there is a network and there is a network operator. Artemis runs in the network, for example, let's say in a VM, and the only thing that the network operator has to do is to configure Artemis, to give a configuration file that includes information about what prefixes are owned by this network and how they are announced in the internet, to which neighbors, how the announced paths look like, etc. In fact, this configuration file does not have to be given manually. It can be also automatically populated. So Artemis has 3 modules. The monitoring module receives input from public BGP monitors like RIPRIs and route views, and also from local routers. So it exploits 2 sources of information. This public monitoring infrastructure has recently started giving real feeds of BGP updates. So whatever happens in the internet and is seen by these monitors, it is given in real time to everyone. So Artemis uses these real-time feeds. And based on these feeds that it receives, it makes some analysis and it can detect if there are some hijacks. If a hijack is detected, it proceeds automatically to mitigation. So let's say about the monitoring part. As I told you, these services are public and the information can be used by anyone. And in fact, they use around 500 vantage points all over the world. So they have a good visibility of what's happening in the routing system. So we would like to have, as a first point, we wanted to see if these monitors are enough to detect hijacks in the internet. So we did some simulations with different hijackers and victims, and we have seen that these monitors are very efficient. So they can detect all hijacks of high impact. So in this plot, we can see that for hijacks that have impact that pollute more than 2% of the internet, they are always seen by these monitors. So if something happens and has a non-negligible impact, it will be seen. Moreover, it could be seen very fast. So we did some real experiments, real hijacking experiments in the internet using the Turing testbed. And this plot shows the detection delay of Artemis. So this is the delay between the time that the hijacker did the hijack until the time that Artemis received the updates and detected the hijack. As you can see, in most cases, the hijack detection takes place in around 5 seconds. And in some cases, it takes place in 1 second, which is in fact the BGP convergence time. Okay, Artemis can see a lot of things and it's fast. But as I told you before, we wanted to design it and be comprehensive and detect any kind of attack. So before going to tell you how to detect attacks, we first have to define what are the possible attacks that the hijacker can do. So we did this taxonomy, and you can think that a hijack attack is a point in a 3-dimensional space. So the hijacker can manipulate in 3 ways the messages, the BGP, and achieve an attack. At first, it's the prefix. It can do an exact prefix or a sub-prefix attack. Then it can manipulate data like black holing, imposture, or man-in-the-middle interception. And the 3rd dimension is the way he can do AS manipulation. So, for example, it can announce a message to its neighbors like this, which we call type 0 hijack, and in fact it's an origin AS hijack, that it pretends that the announced prefix is its own. But because these things are usually filtered by RPKI, it can do more sophisticated things like in a type 1 hijack that he pretends to be a one-hop neighbor of the victim AS, while this link does not exist in reality. And if there is a type 2 hijack, it pretends to be a second hop neighbor, etc. So Artemis can detect all attacks in this 3-dimensional space. I won't give you details about the different detection methodologies. You can find more information in the paper. Compared to previous approaches, in the past, different approaches could detect different attacks. But as you can see in this table, none of these approaches could detect all these attacks in the 3-dimensional space. So if a network was using one of these approaches, then a hijacker could find a way to evade this detection system. Now, about accuracy. This table shows the false alarms given by Artemis for different hijack types, which are different rows. So, for most types, Artemis, by design, returns 0 false positives and false negatives. So, we did not measure it, it's by design what it happens. And this is because it leverages the local information, because Artemis is used inside the network, so the network operator configures the system. It has full knowledge of what happens locally. And this allows to have 0 false alarms for most types. However, for some sophisticated types of attacks, like exact prefix hijack, and at the same time, when a fake link appears 2 hops or more far from the victim, in this case, we cannot use local information because locally we don't know what happens 2 hops further than our network. So this is a hard problem to detect these attacks. For this problem, we designed some algorithms that take into account past data seen all over the internet, and we compare this data with currently received data, and we do also some impact estimation. So the performance of our detection algorithms, we did real experiments and found that they have low false positives and 0 false negatives. Moreover, these low false positives can go even lower if the network operator decides to neglect some events, some alarms of low impact. So for example, if there is a suspicious event that only one monitor saw it, the network operator can pre-configure Artemis just to neglect these events in order to decrease the alarms, the number of alarms. But it is up to him, it's his decision. Now, after the detection happens, the next step is mitigation. So, what Artemis does is that it proceeds automatically to mitigation. And why it can proceed automatically? Because at first it does not give false alarms, or the network operator can pre-configure, depending on the type of alarm that Artemis gives, what are the next action. So the network operator can in advance decide what he will do, and Artemis will do it automatically. So there are two options to do the mitigation. The first option can be done only by the network itself, and it's the aggregation. In the aggregation, the network announces more specific prefixes, which are preferred from other networks, and attracts back all the traffic of the hijacker. So the hijack is entirely mitigated. Now, this thing does not work when the hijacker attacks a /24 prefix, because more specific prefixes do not propagate in the internet. In this case, the network operator has two options: either to do it by the either to act by himself, which has limited efficiency, or to get help from other ASs. And in fact, the method we propose is similar to some practices that happen now, so it is feasible. So we propose that there is an outsourcing and another organization that announces the prefixes of the hijacker and attracts the traffic, the prefixes of the victim, attracts the traffic from the hijacker and tunnels back the traffic to the victim. And in fact, these services are used now in DDoS mitigation. And these companies, you can see in the results for them in the blue box, they already offer these DDoS mitigation services. So we check their accuracy, their efficiency, when if we applied such a mechanism for BGP hijacking mitigation. So we can see they are quite efficient. And finally, we did also real experiments to see how fast the mitigation can be. And in fact, the mitigation is fast because it's automated. And this plot shows in the y-axis the number of monitors that are polluted, that route traffic to the hijacker. And this is the y-axis. And the x-axis is the time. So at time 0, the hijacker does a hijack. So a lot of monitors get polluted. Then Artemis receives a message from a monitor, does the detection, and starts the mitigation. And then monitors come back to the victim because the mitigation happens. And as we can see, all monitors turn back to the victim within 60 seconds. And I think this is the main message I want you to keep from our approach, that Artemis enables the neutralization of hijack, and neutralization, I mean the detection and mitigation, within a minute. And with current practices, now this happens within hours or even days in some cases. So we bring it orders of magnitude faster. So summarizing what we did, we designed a BGP prefix hijacking defense for networks. And our design was based on the needs and the requirements of network operators by seeing what they do now and how they do it. And our approach has some advantages compared to previous approaches. It has no third parties involvement. It's fast within a minute. It's accurate, 0 false positives, comprehensive, all types of attacks, flexible, and privacy preserving. So now, as a part of our ongoing work, we are in the process of open sourcing a tool based on Artemis. And in fact, we are in the process of co-designing this tool. So we go to network operators and we test it with them to see what they would like in order to make it more practical. So our aim is that we build a tool that network operators will use. And I would like to thank you and thank also my co-authors in this work. We are here from Forth or from CADA. Thank you.
Pablo, thanks for the talks. Very interesting. So maybe I missed it, but I'm sure you are aware of FlowSpec in BGP, which is FlowSpec, which is a mechanism to mitigate DDoS attacks even in non-adjacent through non-adjacent ASs. So I was wondering, is it for the mitigation part of this, is it complementary to FlowSpec? Is it relevant? Is it something orthogonal? Do you know?
So our first approach, what we have proposed and tested with simulations, because let me go here. Okay, so this is option 2, right? you were referring to something like this. Okay, so we proposed this mitigation method because this is something that is similar to what is used now in industry. So we believe, and in fact we had conversations with network operators, that they believe this method is practical. Of course, Artemis can support many other different methods. You just have to plug them into Artemis. So it's a different mitigation method that can be selected as an option by the operator.
I guess my point is that my understanding is, and I'm not an expert in this, but my understanding is that FlowSpec is a mechanism within the protocol to actually inform ASs of malicious sources of traffic, which is, okay, it's not hijacking exactly, but is a source of DOS. And since you're saying that you want to open source Artemis, I was wondering whether you could exploit similar mechanisms within the protocol for the detection and mostly the mitigation of adversarial events.
Okay, see, so thanks for this suggestion, for sure, we'll look for it. And the thing here is, I'm not sure, I have no idea about how many people use FlowSpec, so, yeah. So we'll look into it, and if there are a lot of people that are using it now, for sure. Thanks.
For FlowSpec, if you want to do the interdomain, you need cooperation. I think this scheme does not need cooperation. I think there's a big difference.
More questions? Well, I look in the slide, it says degrading, right? Reacting by degradation, but degradation by itself might be perceived as a hijacking attack, right? So if somebody tries to protect by degradation, probably some other AS can decide that it's an attack in itself.
No, the deaggregation is done by the victim network. So if there is a victim network that announces a /23, and there is a hijacker that hijacks this /23, the victim can announce /24s.
Okay, so degradation by the
by your own. It's like you're doing traffic engineering, splitting your prefixes.
Okay.
So, for example, this could be filtered with RPKI if you have not declared your prefixes there. But if you know that you're going to do this, you can pre-declare your prefixes in RPKI, so there is no limitation.
Okay. And you're looking at the overhead as well, right? Because some people are concerned about the number of prefixes, right? So if the protection by deaggregating prefixes by origin ASs, then it's even more ISs need to be supported.
This countermeasure, it's temporarily. So what network operators do now in order to solve hijacks, they usually call other networks and say, please filter your customer because he's hijacking me. So what Artemis can do is automatically deaggregate, solve the problem for now, and then the operator, while has the problem solved, can call, filter, the other operator filters, and when everything is okay, he can go back to the normal announcements.
And let me just ask a question, because also when you're motivating your work, right, and says, well, schemes like Cyan are too complex, right? They change the routing fundamentals, right? It's difficult to deploy, but you know, Adrian's talk, there was also examples of actual deployment, right? You can look at in Switzerland, and actually the thing is not very fancy and very different, but actually it's deployed. Or you look in South Korea. So what about Artemis? Do you have actually experience with the ASs that actually want to deploy it and use for protection?
We are talking with operators, and in fact, a part of Artemis, for example, if you use only the detection thing, it does not involve with your operation. You just have a fast detection alarm. So as a first step, what we are doing is we are testing this with some operators. So we are in the process of building this prototype. So in the next few months, I think we'll have some testers.
So it seems that option one obviously works, but obviously the attackers can simply advertise /24. So then, how long do you think it takes if you deploy Artemis? How long do you think it takes until you're only left with option two?
What do you mean? How long?
I mean,
in the deployment?
As an attacker, I mean, attacks evolve, right? If I really want to attack someone, I'm not going to use the lamest attack. I'm going to use, state-of-the-art attack.
You can go directly to /24.
Yeah.
So, for example, for these cases, I mean, it's up to the operators. They can pay another company, for example, like the DDoS mitigation companies like Cloudflare or Akamai, and they can head in advance this system. So whatever happens at that time, it turns automatically to the mitigation by this outsourcing mechanism. So in terms of implementation, the feedback we got from operators, it was really good that this approach can indeed work because they have tested with DDoS mitigation. So they told us that, yeah, it's something reasonable.
Hi, can you hear me? Yeah. So I was just wondering, because probably when you have an attack, you attack multiple prefixes and they impact the network differently. Have you looked at sort of prioritizing that list of prefixes that get hijacked? Because as Sergey was saying, the aggregation is so like negative perceived in a sense. So, you know, when you apply that, maybe you want to prioritize it, like the aggregate prefixes that like bring a lot of negative effects to your network being hijacked. Does that make sense?
I didn't understand really well. Let me say, so you mean that if you are get hijacked in different prefixes, to do mitigation only for one?
Yeah, exactly.
Okay,
like
yeah.
the one that has like more impact. Obviously, that would need like input from the network, but I would assume that's very powerful.
Yeah,
Did you
exactly.
consider that?
So as I said, but I didn't get into details, Artemis, it's totally configurable. So for example, if you are a network and you have a prefix allocated to a bank and the prefix allocated to, let's say, a dummy web page, you can say, okay, if a hijack comes for the bank, do it automatically. If a hijack alarm comes for the dummy web page, let me check what I'm going to do. So you can configure it per prefix, per type attack, per impact, etc.
Okay, let's thank Pavlos for the presentation. The next talk in our security session is by Anat Bremler-Bar. She's from associate professor at IDC in Israel, and actually she graduated with a PhD from Tel Aviv University, and she's a kind of a proof of what Andrzej told earlier in the talk. So even though we have fundamental scientists, they're also very practical. So at some point in her life before joining IDC, she was co-founder, chief scientist of Riverhead Networks, which Cisco acquired. So that's an example of practical innovation combined with excellent science.
Okay, so I will talk about deep packet inspection. This will be an overview on the subject. In 2010, I founded a Deepness Lab. Deepness is DPI for Engineering for Enhanced Performance of Network Element Security System. Yotam, my former PhD student, had invented this cool name. And you can see the whole publication in the site. I co-founded it. I was the PI of Starting Grant. And it was with collaboration with Professor David Chai from the Hebrew University. Over the year, the group was more than 20 master PhD and postdoc students, more than 40 papers and several patents. Currently, in the lab, we have 1 PhD and 2 master. Here's a picture of one of the group meetings. This is the picture of my former postdoc and PhD student, which I'm very proud because they continue to postdoc at cool places like Princeton and Berkeley, or continue to be in a leading position in a startup company in Israel, chief scientist and co-founder and CTO. And the surprising was for me that we had a reunion here in SICOM. I came with the current PhD student Lior, and then I met Yotam, Shir, and Liron, and we again were all again in the same place at SICOM. They had talks in the workshop. So, what is deep packet inspection? Deep packet inspection is a technique to classify traffic. You classify according to the packet payload, the data, against known set of pattern, which can be string or regular expression. And if it matches some specific pattern, you have the corresponding action. For example, if there is evil in the message, drop the message, okay? So it's very custom in network function, what a few years ago we called middle box, and now it's network function. You see here example in snort, regular expression, snort IDS, claim AV, antivirus. And basically, almost all the network function use DPI. It's used for traffic shaper, load balancer, firewall, and many of them are security systems. So, DPI, why I'm talking about DPI? Because DPI is considered to be a system bottleneck, which is surprising because when I describe it, it's a well-known and well-studied problem in computer science. But the theoretical solutions are not sufficient solution to the current demands. And we have hundreds of academic papers over the recent years dealing with scalability, throughput, latency issue. So I will talk and dealt in the ERC with several challenges and also opportunities. And the challenges are the scalability, because you need to deal with 10 or even 100 of gigabytes per second. And the memory requirement, because you have to handle thousands of known set of patterns. And the traffic is also becoming more complicated, not just clear traffic, also complex traffics. And because DPI is a so important component in security mechanism, you need to be also resilient to attacks, especially DDoS attack. But there is also opportunities. DPI in software-defined network and network function virtualization help to design a better system for handling the challenge of DPI. And basically, this will be an overview talk. I will go over all the challenges and opportunity and give you some taste of what we have done and accomplished. So the first challenge was scalability. And bear with me, 2 slides about what is the traditional solution. So traditional solution is the deterministic finite automata. It can be non-deterministic, deterministic, but basically you have a state, you get the characters, you move to a next state. If it's non-deterministic, it's many next state. If deterministic, it's one next state, but the automata is much larger. And this is the problem, because NFA is not, cannot cope with the demand from the time perspective, and DFA, it's just infeasible to build one large DFA. So, what are the solutions now in network function, for example, in Snort? So basically, they use 2-phase approach. First, they look at all the strings that appeared in the combined set of the regular expression, take the string, union them, perform a string matching, and if you find that for specific regular expression, all the substring appeared, then they go again on the packet and perform a single match with a single regular expression. Okay, so they build a single DFA for each regular expression and run it as a second pass if the string of the regular expression appeared. So what is the problem then? So the problem that you need to deal with string matching. But string matching is not just a so easy task. Because string matching, you build DFA, okay? And again, you have the problem of the space. Because DFA, you need to have the state, and for every state, every possible characters. So the size of the DFA is huge. For example, in Snort, is you see 73 megabyte, and in claim we around 1.5 gigabytes, which means that you are also too slow because it cannot fit SRAM. Okay? So our first work dealt with compaction of the DFA, and the cool observation was that the name of the state is really meaningless. You can choose the name as you wish. So we choose the name of the state cleverly, so we could compress, you can see here the original DFA and the compressed form, and we compressed the DFA such that for every next state, we have only about one rule. This is achieved by the fact what we encoded all the current states that with the same characters go to next state with one prefix. And you can see that the compaction we achieve is very impressive. Okay, we reduce the space by the 100, which means that we can use fast memory. Actually, what we have done, we reduce the problem of pattern matching to the non-problem of IP lookup and longest prefix match, what routers perform. And for IP lookup, you have chips that know to perform it in high speed. And for example, we use TCAM, which is a fully associative ternary memory, which is very common today routers, and implement the DFA of string matching on the TCAM, and by this achieve a high rate and low memory requirement. So next, I will give you a taste about the next challenge, dealing with compressed traffic. So compressed traffic is very common today, especially compressed HTTP. 76% of all traffic is compressed. And they use it because it reduces bandwidth. The data compression is done by adding reference pointer to repeated data, gzip, which means if you see here in the example, you have here HTML, and then you encode it by saying go back 26 characters and copy 6 characters. And after the gzip, they perform Huffman. Okay? And the problem with compressed traffic, that many of the current security tools do not deal with compressed traffic because the high time challenges in time and space. So I will explain why there is time challenge. If you want to perform deep packet inspection, you first need to decompress the traffic. Why is it? Because HTTP compression is adaptive compression because of the pointers, the bug pointer. The same string can be encoded differently depending on its location in the text. So you must decode decompress the traffic first. So the common belief was that decompression plus pattern matching, it's much, much more costly than doing just pattern matching. So what is our solution? We observed that, in fact, it can help you, the fact that the traffic is compressed. You can accelerate the deep packet inspection. Because if you think about it, compression is done by compressing repeated sequence of bytes. So, store information about the pattern matching result, and you wouldn't need to fully perform again pattern matching on repeating sequence, which already scanned. We receive 2 or 3 factor of time reduction, and the surprising result that decompression plus pattern matching is much faster than performing pattern matching. We then, in the follow-up work, we dealt also on regular expressions and also with SDCH, which is the compression technique used by Google at Android and Chrome. The other challenge with compressed traffic is the space challenge, Why you have a challenge? Because for each session, you need to store a buffer of 32 kilobytes, because the back pointer can be for the last 32 kilobytes of the traffic in the same session. The outcome, that if you are a high-end firewall and you need to deal with 100 of thousands of concurrent sessions, the penalty is huge. It can become even hundreds of gigabytes. So here we observe that the 32 kilobytes for decompression are not used most of the time. You use it only when you receive a new packet for that session. So we took the 32 kilobyte and kept it in compressed form most of the time. And it's some light version of the compressed form of the traffic. We receive 5 space reduction. You might wonder that there is time penalty, but if you combine the two approaches for accelerating the time and reducing the space, the overall improvement is by 80% and the time by 40%. So we were so impressed from the results, so we decided to use it also on uncompressed traffic. So in a follow-up walk, we do the other side of the coin. We did acceleration by identifying repetition of uncompressed traffic, because there are repetition in uncompressed HTTP traffic, entire files or part of the file headers. And again, we keep scanning again and again the same thing and surprisingly get the same scanning results. So we did a mechanism that identify very quickly the frequently repeated data, perform DPI on the data once and remember the result, and when encountering repetition, recover the state without rescanning, and we again achieve a boost in performance. The third challenge was securing the DPI. So why we need to secure it? So it's important component in firewall and network intrusion detection system, that their goal is to identify malicious packets and stop them and let the normal traffic pass. But then if the deep packet inspection is not secure enough, the attacker can do 2 steps of attacks. First, he will send heavy packets that are hard for the DPI to inspect, kill the IPS and the firewall, and then launch the original attack when the IPS and firewall are out of the pictures, and bypass them. For example, steal credit card. The Sony attack was such combined attack. They first do DDoS attack on security element, and then they went and steal the customer information. So why DPI is vulnerable to attack? So basically, if this is the DFA, usually in most of the algorithm, the performance you received is because you only deal with the head of the DPI, which is in the cache memory. You enjoy the locality. And if the attacker knows the implementation, it can reduce the locality, getting the DFA out of the cache, and making it much slower. How much slower? You can see here heavy packet rates and the throughput, and you can see that you can make the DPI much, much slower. So here we decided to present a multi-core or multi-VMs, there are 2 variations, of system architect, which is robust against complexity DDoS attack. And the basic idea is that there are DPI algorithms that are more stable. This is the red one. But their performance on regular traffic is much less than the used algorithm. But if there is attack, they are stable and the performance is much better. So we built a system where some of the core, or you can see some of the VMs, run the red algorithms that deal good with heavy packets, and the others run the blue algorithm that perform best for regular traffic. And we built here a mechanism that quickly identify heavy packets and move them to the cores that are dedicated to packets that heavy and makes troubles to the system. And you can see that we got a good result. So now the opportunities. What bring to the table SDN and NFV? And if we think about SDN and think about service chain, traffic passes through several service chains, and each of them have its own DPI. This means that each packet is scanned multiple times, which costs waste of computation resource, because you scan the packet against a pattern in each of the network function. So it also complicated building network function, because you need to build your own DPI, you have the cost of implementing it. So our solution was to suggest DPI as a service, take the DPI out of the network function. All the network function will send the patterns to the DPI as a service. The DPI as a service will perform once the DPI, will write down the result, head it to the packet, and send it to every network function. So why it's so helpful to have a centralized DPI service instead of multiple instances? Because you get much more innovation in network function, because you take the complicated stuff of DPI out of the design. It reduces cost because you perform it only once, and it's the network function in many cases the bottleneck. It improves performance because you scan each packet once, and it's beneficial because the time requirement is sublinear with the number of patterns. Think about DFA. You have the state, you have the next state, according to the character. It doesn't really matter how much patterns you have at the set, okay? And you can design it with rich functionality because you have DPI as a service. Spend once about thinking how to build DPI, and all the NFA network function will enjoy it. So from the architecture point, you have a DPI instance. It can be one or multiple. You have the controller, which receives the pattern sent from all the network function and divided if you have multiple DPI instance, if you need to run more than one DPI instance as a service. And you have mechanism to pass in the result. The mechanism can be a network service header, and you can see here the cool animation. And then you will do the DPI, and you will send it to the all network function in the service. So what next? I'm near the end. 2 years ago, we had a paper at SICOM, which basically was with the observation of Yotam that most network functions do very similar processing steps, not only DPI. They do also header classifier, all of them, and you can see here an examples. But there is no really reuse. So OpenBox is a framework which is based on this observation. You can see the details in this page in GitHub. It's a little bit even much more. It's a new software-defined framework for network function. You decouple the network function control from their data plan. You have OpenBox instance, the OPI. which is the data plane entities, which can be DPI, packet classification, or others. You have an open box controller, which is the local logically centralized control plane. And then you write the network function as open box application on the top of the open box controller. And you achieve a lot of benefits. I will talk only on the first one. You have unified control for all the network function, because today in network function, every network function has its own control. Now you have a unified control, again, better performance, scalability, and stuff like that. So conclusion, DPI evolving area, SDN and NFV changed the field of network function, and among other, the DPI area. Thanks.
Yes, let's go here.
Hi, Lucas Gensler from Electrolux. I am curious, in the scenario you described where you do the DPI centrally and the packets are basically inspected only once and then it's replicated. So how do you actually know that it is the same packet at the other switches or at the other nodes? How, you know, that it's an inspection on its own to know that this is the packet that has already been inspected somewhere else?
You're referring to the fact that the packet may be changed because you send the same packet. It's the same. You don't duplicate the packet. It's the same packet. You just go first to the network function. There it performs once the DPI, and then you write down the result and go to the whole network function with the result written on him. If you're referring to the fact, okay, there's some constraint that if someone will change the packet because this is the action, but this is a very special case, not a custom case.
I have a question. Most of websites have been encrypted by using HTTPS. How to solve this problem?
Yes, encryption is a good problem. Your Tom, I think, has a follow-up work about dealing with this aspect. But you know, encryption, or you have the key, or from the fact that it's encrypted, you cannot perform the packet inspection. It's part of the fact that it's encrypted. So there are still a lot of deep packet inspection because many of the headers are not encrypted. Before the encryption, they are not encrypted. Most of the DNS is not encrypted. So deep packet inspection, also on regular traffic, is very custom in network function. But yes, sure, encryption is a huge challenge.
Hi, I had a question about your compact finite state autonoma. So you mentioned you use a prefix-based solution to compact it, right? And you mentioned that you could use a TCAM for implementing. How do you envision the use of the TCAM? Because I understand, so systems like Snort run on a general purpose processor, and you're right that in the routers, usually you have TCAMs, but in the routers, it's also very difficult to have enough, let's say, bandwidth to process all the bytes of your packet. So how do you plan to use a TCAM?
Yes. So basically, when I started the grant, also in the proposal, my vision was that if you reduce it to IP lookup and you have off-the-shelf chips of IP lookup, and if you will show that there is a real advantage of using it, someone can take and build a card with the chip on it, okay? So this was the vision. And this is the first step to show that TCAM is mostly useful. If you think about a GPU, okay, they started as something with very purpose goal, and then people start to use it to other things. By the way, when we started, we had a very good connection with NetLogic, which was the largest vendor of TCAMs, and then they were bought, and we have discussion about this with them.
So my understanding is that the compaction technique will work for such a specialized hardware in a sense, but you cannot use it on a general purpose CPU, is that right?
Yes, but if you think about it, there's also a lot of work was done also on performing IP lookup in a scalable way. So just the fact that you find equivalence between the problem can open you doors also from the software perspective.
Okay, let's thank Anat for the presentation and move to our, and move to the last talk of this session. We're running a bit late, but our lunch slot is long, so everybody will have enough time to eat lunch. So our next speaker is Serjan Chapkun, and he's a native of Croatia. He graduated with ECS degree, diploma from University of Split. And now he is a colleague of Adrian at ETH, and I think it's our similarities. Looks like in Switzerland, they train people at the EPFL and they end up working as professors at ETH. In between, he was at UCLA as a postdoc, also worked at the University of Denmark. And he's, in addition to security, he also kind of starts a little bit of a wireless theme, which can continue later in the day.
So, is there a way to plug this in? Is there like a power plug somewhere or electricity? No? Like, okay, hopefully my laptop doesn't die in the process. Might die at 20 minutes or so. Okay, so I guess I have a strict limit. In any case, I'm speaking last in front of a bunch of hungry computer scientists. So let me try to move fast. So my project is about securing positioning. So this is something of a little bit of a off-the-side topic in networking as well. So let me try to illustrate it with an example. So me and my car, I keep my car keys in my pocket. I approach my car, and my car matches me a box. Right? This is a case that we experience every day, pretty much with all modern vehicles. Right? However, how does my car know that I'm getting close to it and that it should actually open? Well, it knows because there's a key in my pocket, and somehow the car and the key communicate, and they figure out that they are close to each other. Now, the problem with this, and the problem how this was implemented for over 10 years now, is that if you just get close to the key, amplify the signal, and then relay it to the car will also know. So this means that if your key is indeed in your house and your car is conveniently parked outside, a pair of thieves can just take two antennas, get them close to your window, excite the key, relay the information, open the car. Right? And guess what? This is exactly what we did in 2011, and largely this kind of relay attacks installed.
Yeah, we're low on time, so it was excellent talk by Sergeant. So let's limit the questions, maybe 2 at most, and leave all the others to talking to Sergeant in person over lunch, which will immediately follow. So if anybody wants to ask a question, or we just go for, okay.
I ask a general question. So you mentioned that you did some standardization effort. The question is whether ERC, this evaluation scheme will help or promote such a standardization. I mean, if it is, the other scheme might be, yeah, I don't know how you formulate this. No. When you are applying, how you phrase this standardization?
I can tell you honestly, when I applied, which was what was this 2016, then I mentioned it in my proposal, but then I honestly I had no idea what I was getting into, because standardization is it really takes a lot of patience, but ERC helps tremendously, because then I can dedicate time to do this, right? And this is otherwise, if I'm running after X sources of funding, I mean, this would have been, and it gives me enough resources to also ask my team to contribute to this standardization effort, because I do think it's important in the end, right? Yeah.
Okay, so I think it's a good moment to stop and continue over lunch. If you haven't been here on Monday, so to get a lunch, you go out, down the big staircase, and go to the right to the restaurant of the hotel, to cross the restaurant. Have your badge either black or dark. It's probably better to take, so Hungary is a safe country, but you never know to spoil your mood at the last moment, right? So after, we start at 2 o'clock, and we change session chairs, so Fernando will be the one chairing routing and programming session, and Antonio will be chairing the wireless session, the last session of the workshop.